Presenting for us tonight is renowned Canadian geomatics professional, Dr. Robert Radovanovic. Dr. Radovanovic has been involved in the field of advanced positioning and mapping technologies for over 25 years, and is well known across Canada as an expert on the application of GPS technology to land surveying, including developing redundancy and reliability requirements. He's also active in the field of 3D laser scanning and remote sensing, including the use of unmanned aerial vehicles for surveying and mapping purposes. Robert is an adjunct associate professor at the University of Calgary, where he teaches courses on infrastructure asset management, as well as supporting research into 3D scanning and photogrammetry. He is also Calgary Engineering Branch Manager at McKellarney Limited, which is a large engineering consulting firm based in Western Canada, where he focuses on delivery of infrastructure engineering projects in the transportation, municipal, and resource sectors. I now hand you over to Dr. Radovanovic to present his work.
Thank you very much, and thank you everyone for joining in on well, late in the evening on a Saturday. I really appreciate everyone taking the time to attend. What you're seeing up on the screen right now is a bit of a tool that I like to use in presentations called Slido. Unfortunately, it seems that you can't access via the website, but if you do have a phone with that can access QR codes, you should be able to take a shot of the QR code and actually participate in polls during this presentation. So we'll see how that goes. A couple things that I just want to highlight as we go through our presentation today is today we're going to be going through a review of practical GNSS or GPS or however you'd like it for land surveying. And the real important part of this presentation today is that, you know, first of all, surveying is different everywhere in the world. So we're going to go through basically a whole pile of tips and tricks that I've learned over my years of doing land surveying in the field. And I'm hoping that what you're going to get out of the presentation today is handy ways to explain what you're doing to other people. I find that that's often the hardest part in surveying is no one really gets what we do. And as I say, a large part of this presentation today is going to be showing you how I explain things to other people, and hopefully you can take something away from that. Of course, as I say, since surveying is different everywhere, I just wanted to highlight that, you know, we're not going to be getting into any discussions of specifically the land surveying practice in your jurisdiction, or in the Canadian jurisdiction, or in Alberta in particular, where I'm at, because the rules and regulations are different everywhere. The intent here is to have kind of a broad overview of principles that help everybody in terms of surveying better with GNSS. As well, you know, of course, I'm going to be showing some facts and figures and graphs and things like that. I encourage you to take those away and digest them, and, you know, of course, talk to your colleagues and review them if you're using them for your own professional practice, because certainly things will change depending on the jurisdiction and where we're at. During the presentation, if anybody has questions, I've got my eye right now on the chat screen here. Feel free to interrupt me and throw in a chat, and I really encourage getting into discussion that way. What we're going to talk about in the next hour is essentially going through a very, very, very quick GPS 101. We're not going to be diving into the depths of how the receivers work and all of that, but really what we're going to focus on is how do we actually take the stuff that's coming out of GPS and use it for land surveying purposes. You know, how do we know that the data is good? How do we know that we're getting good reliability and redundancy? How do we deal with coordinates and things like that? And then I'm going to close off with a demonstration of a really handy tool for establishing control via GPS that was developed up here in Canada, but actually works pretty much everywhere in the world. So to start, super basic GPS. As we know, GPS measures ranges from your receiver to satellites. And, as surveyors, we often forget that. GPS does not somehow measure a latitude or longitude. It doesn't, your RTK doesn't measure the distance between 2 points, right? A chain or a tape measures the distance between 2 points. Instead, GPS measures the distance between itself and a satellite, right? And that we know where the satellite is. We know the coordinates of the satellite because we have an ephemeris and we know what time it is. So we know the coordinates of the satellite. We get the distance to this receiver. And if we measure one satellite, it means that the receiver could be anywhere on this arc as shown. So what do? We measure to multiple satellites, right? Either we wait, I was mentioned about Doppler earlier, we wait for the satellite to move somewhere else so we can get a second range if we haven't moved. And then we've got two arcs, we can intersect them. We're doing trilateration. There can only be one place on the surface of the Earth that can occur where I measure those two ranges. Now I know my position, right? In practice with GPS, usually instead we actually measure to multiple different satellites, measure those distances, create our arcs, and away we go. Since in GPS we need to know position and time for our receiver, we need a minimum of 4 satellites to be able to actually pull this off in 3 dimensions, right? So we need 3 satellites minimum to get our position, 1 additional satellite to calculate our clock offset. One big question that, again, we forget about is how do we actually measure those distances? And there's 2 ways that a GPS receiver measures the distance between itself and a satellite. And you have to imagine this satellite is 20,000 kilometers away from the receiver. So this is a hugely long distance that has to be measured. And the primary way, the way that works in every handheld, every iPhone, Samsung, anything that's got a GPS chip in it, is you're measuring the code that's being emitted by the satellite. So, we have a number of satellites, GPS, Galileo, Baidu, et cetera, all up in high orbit. These are all transmitting a unique code, right? They're sending a pulse, a signal that's got a unique code tied to that particular satellite. And the receiver that you have on the ground knows all the codes. It knows what code satellite number 6 generates. It knows what code satellite 24 should be generating. And if we assume that the time of the satellite and the time of the receiver are synchronized, everybody's sending stuff at the same time, what would be happening is the satellite would be sending out this code, the receiver is generating its own version of that, and the satellite not only generates its own code, it's also listening to the code created by the satellite, and it knows, okay, I've got to shift those 2 codes so that they overlap. And the amount that the codes have to be shifted from what the satellite's hearing is the distance to the satellite. Now, a couple interesting things about the code is that, I've just gone the length of one of those, the shortest length in the code is about 300 meters if we take a look at time times the speed of light. An important property is usually a signal processor can only measure to about 1% of the smallest interval. So if the length of the chip is 300 meters, the DIT is 300 meters long, I can only correlate things to about 1%. So the best I can measure the distance is about 3 meters. And that number is getting a little bit better as receiver technology is improving. But to give you a baseline, when I'm using a handheld GPS, the best I can even measure to a satellite is on the order of a meter. I can never measure to the centimeter or to the millimeter a code range to the satellite. Another property of the code is that the whole, as I said, every satellite's got its own unique code, versus that code is about 1 millisecond long. And so that's about 300 kilometers in length, right? If I could take that code and see how long it's stretched. So that means to be able to, every time that that repeats, I might be 300 kilometers off in my overall distance, but generally you generally know your location to about 300 kilometers anytime you turn on the receiver. So you can properly figure out which version of this whole repeat you are. So when you're measuring with code, you don't have any issue with things like ambiguity resolution. On the flip side, we also measure with GPS receivers something called the carrier phase. And what the carrier phase is, the code, as I said, was the di-di-di-di. The carrier, like an FM radio, is the base sine wave that everything's built onto. So the satellite is sending this signal as a wave through space. The receiver can generate its own version of that wave. So the whole principle is exactly the same as it is with code measurement. I have to shift these two waves together until they match, then I know the distance. The advantage of the carrier phase is that the carrier wavelength is only 19 centimeters as opposed to 300 meters. So again, if I use my 1%, it means this receiver can measure the difference in the carrier phases to an accuracy of a millimeter as opposed to meters for the code. But the problem is that every wavelength looks the same as the other. So I don't know if I've got 27,000 waves between me and the receiver and 0.01 wave, or if I have 52,000 waves, 0.012 between me and the receiver. I've got this unknown number of full wavelengths. And that's what we always call the ambiguity that we have to resolve when we're using the carrier. So the important thing to remember is we got two measurement things: code, which is big, coarse, inaccurate, but reliable. And we've got carrier, which is fine, precise, but difficult to remove the ambiguity from. Now, with those two measurement things, one of the big questions that I always get is, a RTK GPS set up here in Canada costs, let's say, $40,000. A handheld GPS, a Garmin, costs $400. So a 100 times price difference. And I always end up getting farmers asking me like, oh, you surveyors are so expensive. I don't know why you're so expensive, because, I have my iPhone that shows me my location. It works the same as your GPS. Why on earth do you charge $200 an hour when I could have iPhones for $200? And the way I explain how precision GPS works looks like this. Imagine that I take two Garmin receivers, handhelds, and I put them on two fence posts, and I just let them sit there. So I know they're not moving. I got one GPS here, one GPS there, and I watch over time the position. So they shouldn't move, but because they have error in what they're measuring, I'm going to see that the position seems to wander for these two. Now, if the errors are completely uncorrelated, what happens is over time, the apparent movement of one receiver doesn't match at all the apparent movement of the other receiver, right? So I can't predict, oh, cool, on GPS receiver 1, it seems to have moved a meter north, 5 meters east. That doesn't tell me anything about, at that moment in time, what the apparent error in the other receiver will be. That kind of error regime usually happens when we have things like noise, multipath, and receiver clock offsets. Types of errors that are completely independent of location. And so I can't mitigate those by having two receivers running at the same time. On the flip side, if I have a lot of correlated errors, what I'm going to see is my two receivers seem to move in sync, despite the fact that they're not moving because they're sitting on two fence posts, right? So over time, they're both moving together. And if that's the case, that is through things that are error sources that are correlated with location, like tropospheric error, ionospheric error, or satellite orbit error, satellite clock error, right? So anything that will affect both receivers somewhat equally. Now, the cool thing is that if I have correlated errors, right? So if I have uncorrelated errors, I can't do anything. Like the accuracy of GPS will stay the accuracy of noise multipath receiver clock. If they're correlated though, what I can do is I can say, hey, wait a second, I know this receiver wasn't moving. I know it says that it's 1 meter north, 3 meter east. So that must be the error. Well, if I say that that's my base station, then what I could say is then at the rover, at that particular moment in time, I must have the same error. So if I could transmit in real time the fact that I'm out 1 meter north, 3 meters east from my base station over to my rover, I could back apply that correction, and suddenly my accuracy would be much higher, right? So now I'd actually be doing differential positioning because I'm taking data from one base station that I know is fixed, transmitting it to the rover, and then back applying that to remove all the correlated errors. That then results in three main positioning modes that we see when we're surveying with GPS. One of them is what we call autonomous, so single point, handheld, your here position when you set up a base station. And the major errors that affect that one receiver just sitting on that fence post, is things like satellite clock, satellite orbit, and your code multipath, right? So multipath is the fact that a signal is not coming purely from satellite straight to receiver. That would be the shortest distance. Instead, it bounces off of things in the environment and corrupts the signal that the receiver is measuring. It typically makes it look longer, right? When I combine all those errors and the fact that I can only measure the range to about 3 meters as it is, that tells me that the best I can ever position with a autonomous GPS receiver is about 5 to 10 meters globally. Now, certainly people say like, oh no, you know, I 100% can get 1 meter accuracy with my phone or with my Garmin, but that's not real, right? That's an observation. If you sat there long enough, you would inevitably see your GPS receiver wandering around at that 5 to 10 meter level horizontally. It's important to note that generally in GPS, my vertical accuracy is about 1.5 to 2 times worse than the horizontal. The second way we typically measure is, as I say, with my fence posts, applying the receiver from applying the error from the base station to the rover is called code differential GPS, right? So now I'm trying to remove my correlated errors, but I'm still working with that code measurement. In that case, the remaining things tend to be atmospheric delays, code multipath, code noise. And the accuracy that I can get is usually then about 0.1 to 3 meters with respect to the base station, right? And then the highest level of accuracy we get with GPS in a real-time mode is when what we call fixed carrier GPS, when now we're actually measuring on that carrier phase. We still have the same kind of errors. We still have atmospheric errors between base station and rover, but now we're dealing with something called carrier multipath. So we're measuring how much that carrier phase is bouncing around in the environment. And we're looking at that, again, much higher level of accuracy in terms of measuring the carrier phase versus the code, right? So instead of 300 meters, 19 centimeters, right? And 1% of that. In that case, our accuracies go down to about usually 1 centimeter plus 2 parts per million. 2 parts per million, meaning for the distance between the rover and the base station, that's my distance that I'm using. 1 ppm is usually 1 millimeter per kilometer of separation, right? You know, is RTK GPS ever a sub-centimeter level system? No, right? It's fundamentally got a base at about 1 centimeter. That's as accurate as you can really possibly get between base station and rover. And then it starts to get worse and worse as that rover starts to move away from the base station, because as shown here, the atmosphere starts to decorrelate. So the receivers here, that if they're close together, see the same kind of error through the atmosphere. When this receiver moves over here, it sees a very different type of error, so you can't just subtract them anymore. That becomes ineffective. Now, one of the things I've found is really important is actually thinking about the accuracy of GPS and the accuracy of survey. From a GPS receiver positioning perspective, the accuracy of your GPS positioning is due to two factors, right? We've already looked. The first one is simply how accurately can I actually measure the distance from receiver to satellite, right? The range accuracy. How big is my multipath? How big is my tropospheric error? How big is my ionospheric error? But the second important thing is this precision dilution of precision, right? So you take how accurately can I actually measure the range, let's say 5 millimeters, and then you multiply that by a geometry-based number, right? That tells you how does that error propagate into the overall 3D positioning error for whatever you're measuring, right? And PDOP usually gets smaller, which is better, the more satellites you have, right? Because the more satellites you have, the more you're averaging out the error of any particular measurement. But it's also heavily dependent on your satellite geometry, right? So having lots of satellites is good, but if they're all in a very narrow slice of sky, then they don't actually contribute as much as having 4 well-positioned satellites, right? It's the same as a network adjustment if you're using an EDM. Would you rather have your control points located all spread around you, or would you rather have, 3 times as many control points but with a bad geometry? Obviously, you want the control points spread around is going to give you more bang for your buck there. So that's kind of the concept of how we actually determine the accuracy of the GPS itself. But one thing that we forget about often as surveyors is we're very, if I can say, concerned, interested in how accurate the GPS is, but that's only how accurate the GPS head is. In surveying, I'm actually concerned about what's on the other side of the pogo stick, right? I don't care how accurate the head, like the GPS itself is. I need to know how accurate I'm measuring the boundary marker, the post, the nail, the spike at the end. And in that case, the overall surveying accuracy is a function of the GPS accuracy, plus as well, all the other errors that might be involved, right? So what are some of those errors? Well, the reference coordinates. How accurate did I set up my base station? Are those coordinates correct, right? Because everything's being measured with respect to that. Centering errors. If my base station isn't properly centered over my reference point, I've automatically introduced that error. Pogo dislevelment, as shown here in this picture. One of the things I've found is, where I'm from, RTK surveying, I would say, has almost completely replaced traditional surveying with total station and prism. Now, one of the problems with that is it means that nobody is checking the level of their pogo stick anymore, right? It used to be really easy to check your pogo stick when you had a total station because you can see it, you can see if it's level with the crosshairs. But now everyone just runs around with GPS shooting points. So I find that the level checks are not happening, which means great, you might be measuring that GPS head really well, but if it's completely, if your pogo stick's completely disleveled, you're not actually measuring the correct point at the other end. So important again that we don't concentrate too much on the GPS side of the equation, but that we actually concentrate on the overall surveying side. One thing that I'd like to highlight is in the surveying industry, folks are very often concerned about whether they should be upgrading their GPS receivers, right? And the Leica salespeople, the Trimble salespeople, the Topcon salespeople are always telling us that we have to upgrade our GPS because we've got some new signal available, or there's a new constellation. Oh, I've just got GPS. Well, you should upgrade to a GLONASS and GPS. Oh, you should now upgrade to make sure you got Galileo. Oh, you should now upgrade to make sure you have Baidu. And all of these are really increasing the cost of upgrading your RTK systems. One of the important things to note, as I mentioned before, your overall surveying accuracy is really fundamentally a function of how accurately can you measure the range from the receiver to the satellite. None of these advancements is improving that, right? Fundamentally, measuring your carrier phase measurement is a several millimeter to 1 centimeter accuracy thing Measuring your code is always a 1 meter or so accuracy thing. No amount of new constellations is changing that. As we also saw, having more satellites is better, but only if they're spread around the sky, right? So being able to see 4 satellites because you're under bad canopy, but there's only a little tiny narrow patch of sky that you're actually seeing, is not meaningfully improving the accuracy of your GPS. In fact, unfortunately for surveyors, all of the benefits, the biggest market for GPS equipment is not surveying, it's consumer products, right? Phones, in-car navigation. Those are the places where GPS manufacturers are actually investing their investment dollars. So when we see all of these new modernizations in GPS or new constellations, remember that the real reason that these things are being developed is not to improve the accuracy of surveying, it's to improve the availability and reliability of GPS for people driving their cars in cities, in bad situations, so that they can always get at least some kind of position, right? A person walking around on Google Maps is more than happy with 3 meters position accuracy most of the time, as long as they can get it all the time. A surveyor is probably never satisfied with a 3 meter positioning accuracy. So bear that in mind. The second thing I always try to bear in mind is that when we focus on GPS, we tend to concentrate on what surveying actually is about, right? And the fundamental aspects of surveying don't change just because you pulled out GPS receivers, right? The most important things are still finding and verifying all your monuments that define your boundaries. You have to plant your monuments to define new boundaries. We're still just trying to measure the distances and angles between monuments so that we can determine what those boundaries are, and then making plans, or whether they be paper, PDF, digital, to communicate to people what the sizes of their lots are, how their boundaries are with respect to other boundaries. Surveyors often get very technically focused on, that we're using the best technical measurement equipment, but then that takes away our focus from things like, okay, is what we're doing correct? Like, is measuring this post, is this post in the right place? Did it move because there was a landslide or some shift, or a river's knocked out that boundary? We can't forget about the fundamental purpose of surveying at the end of the day. The probably biggest question I'm always asked is, when I'm using RTK, how far can I go from the base station, right? Everybody, and the answer that everyone wants to hear is as far as possible, right? We want to be able to go very, very far from our base station, because that way it's super handy. I get to set up my base station somewhere and then just go 20 kilometers around picking up topo. In reality, the way we got to think about this is, we know that RTK surveys, first of all, as we saw in the earlier slide, are usually accurate to about like 1 centimeter plus 1 or 2 ppm. And when we're looking at that, that means if we go with a 2 ppm on average, a 10-kilometer shot between my base station and rover is going to be accurate to about 2 centimeters. The survey itself looks like a very long set of side shots from a central point, right? And it's important to note that when I talk about accuracy, I'm always talking about accuracy with respect to the base station. So this 2 centimeters is 2 centimeters accurate at this point with respect to the base station. This point is accurate 2 centimeters with respect to the base station. This point is accurate 2 centimeters with respect to the base station. But usually on a survey plan, I'm not showing a central base station and then these vectors radiating. What I'm showing is I'm showing inverses along what would have historically been my traverse line, right? So the accuracy I really care about usually is the accuracy between these points, right? Not with respect to the base station. And we often forget that. So as I said, if I assume that my accuracies are 2 centimeters with respect to the base station, the inverse between these 2 points would actually be accurate to about 2.8 centimeters, right? 2 times the square root of 2 if I'm just differencing those coordinates. Well, the problem is that 2.8 centimeters is between these 2 points. And if everything has the same accuracy, that means these 2 points are accurate to within 2.8 centimeters with respect to each other. Same here, same here. But notice that accuracy is generally not related to the distance between the 2 points that I'm inversing between. So sometimes I'll end up with 2 points that are very close together. Because they're both accurate 2 centimeters with respect to the base station, the inverse is accurate to 2.8. But if this was only, let's say, 50 meters apart or 20 meters apart, well, 2.8 centimeter accuracy measuring 2 points that's 30 meters apart is not a very good accuracy from a conventional surveying perspective, right? And when we equip crews with RTK, those crews usually forget that total stations exist anymore. And so we'll get people going around surveying points that are 5 meters apart with RTK, survey, 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 survey. But the base station is 10 kilometers away, and they're not thinking in terms of the fact that, hey, you know what? It's the inverses that matter. In fact, if I'm measuring these points, the better way to go is I should be using GPS to establish this point, use GPS to establish a completely different point, let's say 100 meters, 200 meters away, set that up as a back site, turn my angle, and actually then, sure, the relative coordinate accuracy here is 2.8 centimeters, but it's spread over a sufficiently large distance that my bearing is good. And now I've got a high accuracy relative shot from this point to the actual target that I care about, right? And again, we really forget about that when we start to get what I call hyper GPS. Is you got to still think about, if you're trying to achieve a certain intermonument accuracy, how do you do that through a mixture of conventional total station work and GPS work? Another question that folks often ask is, how long should you wait? Like, how should I take a shot with RTK for 30 seconds, 5 minutes, 1 second? What's the impact of how long I wait there? And the trick about that is understanding better how the actual accuracy of the points of the GPS over time is. So GPS errors are temporally correlated. What that means is that points that are very close in time share the similar error profile. As an example of something that's not temporally correlated, that's random over time, take a look at the graph above at the top here, right? So this shows a very rapidly changing signal, right? The error is plus 1 millimeter, minus 1 millimeter, plus 2 millimeters, minus 2 millimeters. Like, there's no relationship between the error at one point to the error immediately after. In such a situation up here, every time I average a sample, they're all completely independent. So the accuracy of my average improves very, very quickly, right? It's because if I took 5 shots, maybe 1 shot's here, 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 and all those errors, because they're all completely different within their band, collapse down, so my average is very accurate. In the case of GPS, the majority of my error in a differential sense, when I'm using RTK, is atmospheric and multipath. And if I'm sitting, those errors change very slowly over time. And you can see in the lower graph here, this is an example of 2 receivers separated by about 3 kilometers. And every second a shot is taken, and how those errors change over time. Note, the graph is in seconds, so 3,600 seconds would be about an hour. And what you can see is that the error kind of hangs out in places, in zones, if I can say, for a while, right? So for here, this is 500 seconds, so 500 seconds, about 10 minutes. Over 10 minutes, the error in elevation here is always about 15 millimeters. The error in elevation, again, for about 15 minutes here is always minus 15 millimeters. So that means in this zone up here, if I happen to be taking shots during this point in time, it doesn't matter if I'm taking shots every second, half second, every minute, all of my shots are going to be contaminated by the same 15 millimeter error. And what that tells me is that when you're surveying, setting your data collection rate to 1 hertz or 10 hertz is irrelevant from a cadastral surveying perspective, right? If we're not doing kinematic type stuff, because you're just averaging the same error over and over and again. And it's interesting. We've done experiments that show, like, if I assume that I come up to a point, set up my RTK, take 1 single shot, and I assume that my accuracy is 2 centimeters, versus if I come up, sit down and hold that, like set up a tripod, occupy a point for 60 seconds, taking a shot once a second, the resultant accuracy only becomes 1.3 centimeters. Now you could say 1.3 is significantly better. It's almost 40% better than 2 centimeters. But I would argue from a surveying perspective, you know, it's not like I'm 60 times more accurate. So why do we usually end up, you know, if I'm surveying things with RTK, occupy things for about 30 seconds? Well, really because that tends to average out the wobble in my pogo over that. It has nothing to do with GPS. It's just I can't hold the pogo steady. So over 30 seconds, I tend to average out that wobble. And that seems to be kind of generally how we get our stuff done. One other thing that surveyors are very concerned about when it comes to RTK is the whole concept of busted ambiguities, of not having the correct ambiguity. And so the whole concept here is when you survey, you usually go out, as I say, you're surveying initially in differential code GPS. So you're seeing your GPS accuracy be to about 0.3 to 1 meter. Then it goes down to start measuring the carrier phase, but you're doing something called float measurements, right? So what that means is, let's assume that this red dot is the true position of a point. And then I'm taking shots every second. If I'm in float mode, what would happen is I would see that every second, the position that I'm recording varies, moves around. And the amount that it moves around is probably going to be usually plus or minus 8 to 10 centimeters, right? Then what happens is the receiver gets enough data that it can figure out how many of those wavelengths are between it and the satellite, and everything collapses down to what I call fixed, right? So now I know how many wavelengths are between me and satellite. I'm measuring that very precise carrier phase. And what I'm going to find is now the variation in that point is only plus or minus 2 centimeters, right? And all the shots I'm taking cluster very close together. But if my GPS receiver had somehow calculated the wrong number of wavelengths between me and the satellite, I would still see that I'm fixed, but I would be fixed to the wrong number of wavelengths. So my solution would be completely out, but not changing. So it would seem that I have a high accuracy level, but I might actually be out 10, 15 centimeters without any way of knowing. And that would be very dangerous from a surveying perspective, because I would think I'm in a very accurate positioning mode, but in fact, I could have a large bias compared to where I'm actually at. And this is the big concern that surveyors have when using RTK. Now, the interesting thing is we did an experiment a long time ago to see how often does this really happen, because receiver manufacturers are making much better algorithms for resolving ambiguities and self-testing to make sure they don't have the wrong ambiguities and so on and so forth. And so what we did was we did an experiment where we took 2 receivers, we put them 3 kilometers apart, we left one as the base station, one as the rover, and what happened was we collected data once a second, okay? Then we had a summer student who stood there and would put a pie plate over the receiver for 1 minute, then take the pie plate away for a minute. So now the receiver could get data, fix, and get positions. Then they put the pie plate back on the receiver for a minute. So now the receiver can't see anything for a minute, and so forth. And they did that for 2 hours, or sorry, 4 hours. It was a terrible job. And the results here are shown. So what happens is, first of all, we got northern easting height over all this time. And what you can see is generally the receiver gets lock, has positions, has a series of these positions, loses lock, so on and so forth. And the overall cluster tends to move around plus or minus, 1 to 2 centimeters over the course of the whole experiment. And we expect that because I said previously that the accuracy of RTK is realistically 1 centimeter plus or minus 2 ppm, right? Twice in that whole experiment, what happened was once something completely weird happened and the receiver just could not, it said it was fixed, but the positions were just moving like crazy. So it didn't converge. It said it was fixed, but obviously the positions were moving plus or minus 5 centimeters. A second time it said it was fixed, but you can see that in what is this? Latitude, in northing, I was out 4.5 centimeters for the entire 1 minute. So this is exactly the scenario that we're concerned about, where for a whole minute, my positions are very consistent, but I'm actually a whole 4.5 centimeters out. The interesting thing is, once we lost lock and got lock again, that disappeared, right? So someone would be very concerned to see this and say, aha, you see, RTK is unreliable because sometimes you can have a busted ambiguity and you might be out 4.5 centimeters, which is bad quality surveying. But I would say, realistically, we only have a 1% chance of ever having a busted ambiguity based on these results. And what's more, if we do a process where we survey by observing a point with RTK, losing lock, reacquiring lock, surveying again, yes, any given time we may have a 1% chance of wrong ambiguity, but we basically have a 0% chance of having the same ambiguity twice. So taking 2 independent shots on the point under different, you have lock, lose lock, have lock again, basically means that you actually will likely have a decent check on that effect as far as your surveying is concerned. All right, and that leads us to the question of what is your best procedure when surveying with RTK to minimize errors? And best is a tough question for surveyors because surveyors hate inaccuracy. They hate to be wrong. So best, if you're talking about most reliable, most accurate, is very inconvenient, right? It's about setting up 2 base stations, you know, not using pogo sticks, always use tripods, make sure that you calibrate your tribrax every day, measure your antenna heights with meters and feet with different measuring tapes, because my measuring tapes are always missing the first 5 or 10 centimeters, it seems, after my chainmen use it for a couple of years, right? So use, you know, break down the base stations, reset them up somewhere else, remeasure the point. You can go completely over the top trying to ensure that you will never have an error in measuring this point. However, for land surveying, really the correct question is, what's the best reasonable procedure, right? And, you know, this isn't going to necessarily be popular, but really what it means is you want to set up a surveying system so that the chance of your error is slim, minor, right? And anytime that you make a mistake, which you will at some point, the chances realistically that the error is going to be significant enough that you get sued is minimal, right? And you can design such a measurement procedure if you think about what the properties of those GPS errors are, right? So around here, the 3 main ways people actually do redundant ties using RTK is, first of all, surveying, and this applies as well to static GPS, is surveying all the points. So you have base station, you go survey all your points, you break your base station down, set up the base station on a different control point, resurvey everything. And what that does is it first of all makes sure that any error in your base station setups is caught, and you will be at those points at sufficiently different times that your ionospheric, atmospheric, and multipath errors have decorrelated. The second way that I've seen people do it is you set up a base station, you go survey all your points, then you make sure you come back, let's say an hour or 2 later, and resurvey all the points. And if you do that, the whole point is you're not catching anything in your base station, but as we showed before, the errors tend to decorrelate over a period of about 20 minutes. So you're going to try to resurvey the points in different multipath and atmospheric conditions. So you're going to actually be meaningfully averaging out errors. The way I think, I would say 95% of surveyors are currently using GPS is you survey you set up a base station, survey a point, dump all your satellites, either by putting your hand over the head or turning it over, however, reacquire your lock, survey it again, right? And the only thing that that's doing is trying to remove your ambiguity resolution errors, but you're not meaningfully averaging any of your multipath tropospheric ionospheric. Now, if your survey requirements are an accuracy of less than 2.5 centimeters, like so 2.5 centimeters or better, then this is perfectly all right, because as we saw previously, the base accuracy of RTK tends to be about 1 to 2 centimeters, right? So surveying twice on a point just simply means you're trying to check those ambiguities. You're not trying to improve the accuracy of the solution. In fact, I think that instead of focusing on the accuracy of the measurement, realistically, we have to more look at what's the impact of errors on survey in general, right? And as I say, in every surveyor's life, at some point, you will have made a mistake. Something bad will have happened. It's impossible for it not to, right? At that point in time, what gets your blood pressure down and actually makes you comfortable is making sure that you can actually go back into your files and know what has gone on, right? You want to actually go back and be able to prove what you did. So this is the concept of traceability, right? And again, I find that because everyone's just following the little rover dot to the middle, we often forget about these things. But in a GPS measurement world, we still need field notes, right? I need to be able to see who surveyed this, when did they survey this, what geoid model did they have, what reference system were they using, what was the height of the base station and the rover, written down on a piece of paper, not just typed in once on the data collector with a mistyping, right? I need to still know, what are you measuring? Very often now, notes are bad in terms of saying, like, was this a bent monument? Was the monument in good condition? Things like that, right? Was the monument wobbly and loose? And as well, recording the raw RINEX data. On every GPS receiver we have nowadays, it is very easy to actually log the raw RINEX data that's being measured, right? And if you're not logging the RINEX data, at least downloading the actual, Leica or Trimble job file. Simply downloading the CSV file of your point stakeout or your pickup is insufficient, because that CSV file tells me nothing about the accuracy or the conditions or how these points were actually measured, right? We need something that we can go back and say, when we surveyed this point, there was 6 satellites. These were the satellites that were measured. This was the PDOP, this was the expected accuracy, things like that. And the second aspect is procedures, right? So simple procedures that really, save your rear when you need them. So one thing we always do is, when we're surveying, you have a base station, you have a checkpoint nearby. Start the day by checking into that point. You go around, you do your survey. End the day by checking out at that point. The coordinates of the point in the morning should not be different than the coordinates of the point in the evening. If they have, it means your base station has, slid over, become disleveled, something like that. But now I've actually got information that I can prove later that, no, it wasn't that the base station was unstable, because I actually know that I matched up at the beginning and end of the day, right? The same as closing out a level traverse, right? Always, you can set up in all of your data collectors now the ability to not allow the data collector to take a shot if you don't have a certain minimum number of satellites or coordinate quality, right? That the receiver here thinks that it's measuring at a centimeter level, great. So I actually set up in all the data collectors that it will not let you take a shot if the accuracy is less than 2 centimeters and if you don't have a minimum of 6 satellites, right? That way I can give this gear to survey crews and I know they're not trying to push it out of the limit. Same thing as I actually always rotate my pogo stick between shots so that if it's disleveled this way at the beginning, it's leveled the other way afterwards, right? And also changing your antenna height at the rover between shots so that you at least have 2 different height measurements as you're going through. Now, one question I'm going to ask quick is, in terms of coordinates, what coordinates, and if the Slido doesn't work, please feel free to type in the chat. What kind of coordinates do folks here typically use? So either folks are using no coordinates, most of your surveying is done just with bearings and distances, or you're using local coordinates, right? So you've got northings and eastings from local benchmarks. And then a lot of surveyors these days are starting to actually use UTM coordinates, right? So UTM coordinates we see being a big problem actually, because engineers don't tend to actually know that UTM coordinates are not actually ground coordinates. Okay, I'm seeing no coordinates in UTM coordinates, which is an interesting split. I'm going to leave this poll active and come back to it here in a moment. But essentially, one of the things that I've seen is, yeah, UTM, is that aside from the physical measurement accuracy of GPS, where we're really starting to fall down as surveyors, or where a lot of our mistakes are happening, is in converting these UTM coordinates into meaningful local level coordinates, right? So as a surveyor, frankly, I don't usually care about the latitude and longitude between 2 points in ITRF in 1996 or 2014, right? What I care is from here to here is a bearing of 256 degrees north-northwest, and the distance on the ground, which is where I live, is 100.2 meters. So, but at the end of the day, I'm somehow using a thing that, you know, is measuring ranges to satellites, deriving latitudes and longitudes, but somehow out of my data collector, I can actually get these relative coordinates I care about. So how's that happening? So essentially there's 3 stages. What happens is, don't forget, the whole thing is first of all working in a global coordinate system, right? So your GPS is fundamentally deriving latitudes and longitudes in WGS84, right? Then inside your data collector, it is converting those latitudes and longitudes usually to a map projection like UTM, right? So now I've got map projected coordinates X, Y. And then what happens inside the data collector is it sets up a rotation, translation, and scale that will convert all of your map projection coordinates into the coordinate reference frame that you care about with the appropriate scale factor so that you're actually measuring at ground. And if any one of these pieces breaks down, then your whole localization breaks down, and these sort of inverses we're calculating, or these local level coordinates we're calculating, become incorrect, right? And there's 2 major pieces to that. So the first is, of course, the map projection scale factor. So, you know, if you take a look at this little diagram here, I've got these 2 points on the ellipsoid. Cool. They've got a certain distance. If I convert these 2 points to a map sheet like UTM, right, I'm going to have a different inverse. And like inversing between 2 latitudes and longitudes is hard for me to do on a calculator, but inversing between 2 map projection coordinates is easy for me to do on the calculator. And what I find is that I can actually go back and forth through this map projection scale factor. Now the trick is, going from ellipsoid to map projection distances depends entirely where I am in my map projection, right? So in the case of UTM, the further I go away from my central meridian, the bigger the ellipsoid to map, not ground, map scale factor is, right? And the scale factor, since it changes depending on where I am in the zone, it means I can't use a single scale factor mathematically for all the points in my network if my network's big, right? The scale factor can actually change by 15 parts per million for 2 areas separated by 10 kilometers in this case. So that means that, like, you know, that's going to end up being 1.5 millimeters on a 100-meter line segment, depending on if I use the wrong scale factor, if I don't change it as my project starts to grow. The second scale factor that's important is the ground grid to, or the ellipsoid to ground distance. So let's assume I've got 2 points here, right? This is at ground level, right? So I've actually taken an EDM, I can measure between the 2, and somehow I assume they're flat. Realistically, if this is the Earth, this orangey dot, what I've got is I got my radius of the Earth and I've got my height above the Earth. This ellipsoid distance, if I can assume the Earth is either a sphere or an ellipsoid at this point, is obviously smaller than the actual ground distance as represented above the ellipsoid. And the equation is quite simple, right? It's just a scale factor that as my height above the ellipsoid or sphere grows, then that scale factor increases as well. And generally, a 10-meter elevation difference will create a 2 part per million difference in the scale factor, right? So I have to kind of assume which shell here do I actually want to refer all my distances, because if I decide to refer my distances to this upper shell, the distance will be longer than at the lower shell. And there's no good answer in terms of which shell here is the right one. Usually what happens is I just average all the elevations for my network region and say, cool, this is my sea level to ground change. Now, if you're working near the coast, that's very minor. I live at 1,000 meters elevation. It's a very major impact for surveying up here. As a concrete example, if you take a look, let's assume we have 2 points here in UTM. And I'm not going to go through the calculations, and if somebody later on wants to let me know if these are right, that'd be fantastic. But I calculate the map distance just from Pythagoras, right? Delta x, delta y, delta x squared, delta y squared, square root, as being 7,070.993 meters, right? So that is on the map plane what the distance between those 2 points are. I can convert those map coordinates to actual latitudes and longitudes if I have a geographic converter. And let's throw in the additional assumption that point 1's at 600 meters, point 2's at 750 meters. Now, if I actually do the geodetic inverse between those 2 points, what I'll find is that the ellipsoid distance is 7,073.758 meters. So the ellipsoid distance is actually bigger than the map distance by 3 meters, okay, on 7 kilometers approximately. If I then scale that ellipsoid distance up to ground, I end up with it being 7,074.513, assuming a mean elevation of 675. The important thing here is that I think we'll all agree, given that I can measure, a centimeter with EDM, that on 7 kilometers, the mathematical impact of how I'm scaling things is way bigger than the actual physical measurement impact, right? So I have to be very careful, for example, not to focus overly on how accurately did I actually measure the distance between these 2 points. More importantly, I have to make sure, am I using the correct grid to ground scale factor, right? If I use the wrong scale factor, I'll have destroyed all of the accuracy that I tried to achieve by carefully measuring something between 2 things. And we see this problem happen a lot when we're using UTM, because UTM is fundamentally it's on the map sheet, and the map sheet doesn't have anything to do with reality, right? If I am just purely inversing points on a map sheet, I might tell someone, hey, you know what, your road is 7,070 meters, 0.993, when in fact, it's actually 7,074 meters for 0.513. Now, you could argue, okay, Rob, is someone really going to care about 4 meters in the difference of a 7-kilometer roadway? No, but I would argue, why am I measuring this to the millimeter if I'm not going to give the correct answer? And also, we have to be aware that when we go to stake out things, if we're just staking out UTM coordinates, we have to be very careful to ask the engineer or whoever's provided us with these coordinates, has a grid to ground factor been applied? How are these coordinates actually derived? All right. If we're working on certain plant sites or in certain areas where we already know the coordinates in a local frame, we often do something called localization. And so essentially what ends up happening is we have a base station with a known latitude, longitude. We survey 2 points. We end up with latitudes and longitudes for those 2 points. These are of no use to us yet because no one surveys in latitude and longitude. But we end up then generating UTM coordinates for those points, which suddenly becomes a little bit more interesting. But then often we'll actually end up saying, I don't want to survey in UTM. Instead, I want to survey in a system where this point is 100, 100. North is defined between these 2 points. Maybe this is the east boundary of a industrial facility, and the whole facility has been set up that between this mark and this mark is due north. I don't care what actual due north is. I'm saying this is due north. So what we end up doing is we set up this kind of coordinate system as a rotation, translation, and scale from UTM, which then lets us, as we're surveying, survey all of our other points automatically in this system. And then I'm just going around surveying and picking up coordinates directly in my local system. Now, there's a number of issues when you try to do that. So the first one is people often will try to recreate. If I send a crew the next day, they will redo the whole localization again, right? So they will actually re-observe these 2 points, create a new localization, survey points a third time. And the problem is, if I'm doing that, I'm not actually using one set transformation. I'm basically using new transformations every day. So there's all these little errors that build up, which is why usually if I go to work on an industrial site with GPS, what I will do is I will spend one day, create my localization, save that, and then all the crews must use that same localization going forward, right? Another classic is using the localization on too large of an area. So I go out and I survey these 2 points, and the 2 points are 200 meters apart. I've got this localization. It's ground level now, great. And then I go 500 meters around and start surveying, or 2 kilometers around and start surveying, and I'm surprised when stuff starts breaking apart. And that's because it's impossible, as we saw before, to have one single grid to ground scale factor that's going to work over an entire area. So generally, we limit one particular transformation to an area of several kilometers, right? And the same thing, often people go do this, and then, you know, they take out an EDM later and they shoot between 2 points and stuff's not fitting. Usually that ends up becoming a scale factor issue, because your whole localization was defined only by those 2 points that you surveyed. So instead, you want to make sure, first of all, that the reference points are outside of the area that you're actually surveying in. And usually I'll always make sure I do cross checks at that time when I'm setting up that control network with an EDM, just to make sure everything fits. Don't trust the GPS by itself. Now, as I said, one thing I wanted to introduce to folks is this precise positioning system that's a service that's actually produced by NRCan up here in Canada. One of the biggest issues that I see with GPS is, how do you establish control, right? So right now, you folks, for example, have, I believe, 5 CORS stations operating around the country. They have published coordinates. So if I'm working somewhere far away from one of these CORS stations, I could certainly, if I'm surveying in the middle, I could set up a base station, let that base station cook for several hours, and then take the Rhinex data from that base station and process it against a CORS station, which has a published coordinate, so that I've now coordinated my survey here. And so now all of my coordinates for my survey will be tied in to your whole national framework, which is good. Alternatively, I might be using some local control, right? I might have a plan that has some published coordinates and such, and be kicking off from that. That works if I intend my whole work not to be integrated with the national framework, right? At the end of the day, I might be doing some local level work. PPP is an interesting service where what happens is I don't need to actually process against a base station or a CORS station. So for example, in the CORS station example, I would download the data for Georgetown. I would download it at 30 seconds interval. I need to have Trimble Business Center or like a Captivate or some sort of GPS-based waypoint, some sort of GPS processing software, and I'd be concerned about processing these long baselines and getting a solution for the base station for my particular job. Instead, with PPP, all that ends up happening is I collect data for a couple hours, I upload it to a website, I get an email back that tells me what the coordinates of that point are in ITRF, and how accurate it is with regards to the national framework, right? And it's very accurate. So for example, in this slide here, what I'm showing is we did an experiment where we actually collected data for 9 months every day for 12 hours. So 12-hour occupations of a fixed point on a building, and doing no GPS processing beyond just taking the RINEX data, which was logged at 30 seconds, and uploading it to this government site. We got latitude, longitudes, heights for that point. No other processing, no network adjustment, no nothing. And we get the coordinates reported back. And what you can see is this is the plot of how consistent the northing easting heights of those points were. And in northing, right, we're within plus or minus 5 millimeters here. In height, we're, you know, plus or minus, let's say, 2 centimeters, which is maybe not sufficient for vertical control compared to leveling, but for most GPS-based applications like topography, it'd be sufficient. And so remarkably consistent, right? Like no fuss, no muss. The way it actually works is you simply go to this website, and the slides to this presentation will be provided. So you'll have access to this website. You go in, you set up an account, you just need an email account. You don't need to be working in Canada. Anybody can set up an account, set yourself up an account. And what ends up happening is you will look up precise point positioning, and that will take you to the precise point positioning tool. From that tool, essentially what happens is you upload a RINEX file. That RINEX file, you don't need the .n file or any other file, you just need the observation file, the .o file. And if it's a very big file, let's say you collected a whole day's worth of data, or you have multiple days worth of data, you can actually just take all those .o files, put them into one zip file, and just open up the zip file, or just upload the zip file. In Canada, our national framework is NAT 83 CSRS, so generally we click on this button, and then that gives us some additional options for like whether I'm working in Alberta, BC, etc., etc. For you, you can collect on ITRF, which is effectively WGS 84, and in that case, all your results will be in ITRF. Don't worry about the vertical datum, because as I understand it right now, there is no geoid model being used, and ellipsoidal heights is what most work is being done with. And I did an example where I was kindly provided with 3 days worth of data from Georgetown. And let's take a look at what the results look like, right? So what ends up happening is you will get an email back from NRCan to your registered email address, and it will have this as a sheet. And so basically what's on the sheet is what time your data started in UTC, what time the data ended. So we can see this is 1 hour's worth of data from Georgetown. As well, we have things like the antenna model. So it's a Trimble 57971 that's on there, which means that the phase center to antenna reference mark is 0.065 meters. Usually I use this just to verify that my RINEX file was correct. And as well, it shows you what the height of your antenna to the marker that you're measuring is, which in the case of the Georgetown monument is logged as 0, right? So it's assuming that, monument is just directly fixed, a GPS receiver directly fixed onto something. The results that are provided are in ITRF 2014 at the current epoch. I see that the latitude, longitude, and height of Georgetown are provided here. As well, the accuracies for 1 hour's worth of data, is it saying that the positioning with respect, this is with respect to the world, right? So with respect to ITRF, not with respect to, you know, the monument that's on the corner of the street or a monument 10 kilometers away, with respect to the whole of ITRF is 1.2 centimeters in northing, 1.8 centimeters in easting, and 6.6 centimeters in height. We're going to see this height gets much better as soon as we get 4 centimeters of, or 4 hours of data. As well, we have the a priori coordinates. So this is the coordinates logged in the Rhinex header. So these are the published coordinates currently for Georgetown. And it shows you the discrepancies, and we're going to talk about that in a moment. It as well shows you then what the UTM coordinates of that point are, along with the point scale factor and the combined scale factor, which is that combining your ellipsoid to ground and map scale factor changes. We see they're both very close, which makes sense because the height is minus 20 meters. I ran this for 3 days. 2 days had 4 hours worth of data. One had 1 hour worth of data. And what you can see is that the results are remarkably consistent. Again, this isn't processing against other core station. This is just dropping a file into a website. And generally, with 4 hours of data, my accuracies in northing and easting are plus or minus about, let's say, 5 to 7 millimeters. And accuracy in height is actually at around 25 mils. And I can see that that's indeed true, right? 5th to the 14th, my results are very consistent. On the 3rd, I've only had that 1 hour of data, which meant for lower accuracies, but I'm still extremely consistent in northing and easting. So what this shows me is that I can just repeatedly take that Georgetown data, or if you have a base station somewhere on your survey office, anywhere on your project site, you could take that Rhinex data that you're collecting while you're surveying anyways, dump it on this site, and actually get a day to day to day to day coordinate comparison of how consistently I guess, have you been setting up that base station. Interestingly, when we take a look at the published coordinate, we see about a 7 centimeter discrepancy in north-south and a 3 centimeter discrepancy west. And I haven't looked into more detail as to why that exactly is, but that's possibly an overall shift between Surgus and ITRF, or an issue of an epoch change between these published coordinates, which are referred to, I believe, 2014 versus 2020 or 2022, which is the current date of processing. And it's also important to note that, you know, ITRF is essentially the same as WGS84 within the measuring accuracy of WGS84 itself. Now, this is handy for establishing control then in faraway areas, because you could essentially drop your base station anywhere in the middle of nowhere and start coordinating. But it also brings up a completely different way of surveying. So for example, normally what we do, if we're surveying across a river, we'd be traversing here, we'd have to move a foresight over here, someone would have to drive around, move the station over here, backside still has to stay on the river, and as I progress, and someone has to go back, pick up the backside again. I'm driving back and forth across this river an awful lot. Instead, what I could do is I could, for example, set up a base station here, let this cook for 4 hours, dump that result into the PPP. So now I know the coordinates of this with regards to ITRF to within a centimeter, survey this point, survey this point, survey all these points with regards to this base station. This is coordinated. Break it all down, take all my equipment, move all the way to the other side of the river, set another base station up, survey more points. And the interesting thing is, because PPP processes everything in the same reference frame, I will be able to feel comfortable that this point with regards to this point are properly coordinated. If somehow I could measure directly between these two, I would get the same result as mathematically inversing between those two PPP positions, right? And so suddenly I can have all of these different survey networks that are not directly tied together, but are coordinated together to within a centimeter and a half. And that becomes really important when we're starting to do things like trying to make digital cadasters of large areas, right? If you want all the subdivision surveys across a city to fit together, this is a methodology that you can use that lets surveyors very easily georeference things without going through the hassle of having to process against CORS data or tie into local control and things like that. However, it does bring up questions of how do we actually then evaluate the accuracy, and like what kind of redundancy? Do I have to set up this position? Do I need to set up twice so that I verify I haven't messed up in using the PPP and things like that? As I say, that kind of concludes the overall of the presentation. I do appreciate everybody coming so late in the evening, but kind of the message that I really want to get across to everybody is that two things. First of all, from a surveying perspective, we've really likely reached the limit of our accuracy, right? GPS will never, I shouldn't say never, but it's highly unlikely that surveying will become a millimeter level technology, right? It will be a 1 centimeter plus 2 parts per million measuring tool, regardless of how many constellations we have. The main improvements are not on accuracy. It's really in terms of availability, performance in urban canyons, performance under canopy in the forest, error checking, and improvements in our user interface, making those data collectors easier. For surveyors, for land surveyors, the message that I keep bringing up is our focus as surveyors needs to be less on the measurement accuracy, and we need to start focusing much more on the concepts of geodesy, coordinates, map projections, because that's where our jobs really break down, right? It's not that we measured something wrong, it's that we converted these coordinates wrong, or we converted them to a wrong datum, or something was rotated with respect to something else, right? And then as well, the other thing we have to look at is we have to broaden our kind of professional scope to start looking at how does the concept of observation, we're used to using levels and total stations, and there's a feeling that I need to basically touch points to measure them. But we're seeing technologies like UAVs and drones and photogrammetry taking a much bigger role in terms of starting to map out cadastral parcels. Well, once that starts to happen, we have to relook at how do we actually define accuracy and reliability. So as I say, I really appreciate everybody's time today. You have my LinkedIn profile. I'll provide everybody with my email address as well. If there's any questions, please feel free to get in touch with me, as I say, either through LinkedIn or through an email, and I'd be more than happy to answer them then. I do see Kamal has one question with regards to RTCM corrections and accuracy. So we didn't touch upon the topic of correction networks, but I would throw out, do surveyors on the line currently use commercial correction services? Does such a thing exist?
The Georgetown Lands and Surveys, you can get their corrections on a receiver, yes.
Okay, so sounds good. So I guess without getting into it too deep, one of the really interesting things is being able to actually, instead of having your own base station transmitting, is to be able to, for example, have a cell phone card in your RTK unit so that you can actually collect corrections from a commercial provider. And in that case, the accuracy is essentially the same as if you were running your own RTK, with a couple provisos, right? So if I assume that my that the correction service has a base station here, if everybody can see my video, the further away I get from my correction service, the worse my accuracy gets. Along the same lines as the further I get from my base station, the worse my accuracy gets. However, a lot of commercial correction providers will actually do something very neat, where they have a network of base stations working, let's say, within a city. So they'll have 6 base stations or 4 base stations working at the periphery of the city, collecting data, and then all that data is combined together to make a virtual base station that is essentially simulating a base station that's very close to wherever you are. So as you're moving around within this network, the accuracy of your correction doesn't degrade with the distance to any one particular base station, because you're inside this sort of ring of corrections. And in that case, you can continue to get RTK accuracies of 1 centimeter or so, but you don't see them degrade as you move around in that geographic area. Hopefully that kind of addresses your point, Kamal.
It does, and I just brought it up because they do have a correction service whenever it's working, I guess, that they can possibly use if they get comfortable with the accuracy.
Okay, and I see a question about having RTK giving like a 10 to 20 centimeter error very close from the base station and commenting on why this might be. So yeah, so as I'd mentioned before, you know, there's your question there is 100% the type of questions surveyors always ask during these presentations. And without any offense, I always call these ghost stories, right? Because what happens is people go out, they measure something, and something weird happens, and you're like, well, that's weird. But usually there's a lack of data in terms of being able to go back and actually assess why that happened, right? So, you know, I've got lots of stories as well where I went and surveyed a point and then came back and surveyed it later and it was 10 centimeters different. But I never bothered downloading the actual raw job file of the first time and sitting down and spending 4 hours to like go through the signal plots to see what might have gone wrong, right? So what I would say is all we can do is guess in your case. So what are some reasons that you might have a 10 to 20 centimeter error? Well, you may have had a particularly bad ionospheric event that caused, as I showed you, you know, 1 time out of 100, you will indeed have an incorrect ambiguity, which would result in a measurement 10 to 20 centimeters incorrect, which you would then discover because you remeasured. So sometimes GPS just doesn't work. I've taken lots of EDM shots, which are weird, and you're like, oh, well, that's obviously wrong. You take the shot again. Okay, that's probably right, and you move along. You may have had another broadcaster stomp on your signal and confuse it. You mentioned it's in the hinterland, so that's unlikely, but that's another reason we see why people have weird results. And so, as I say, without actually seeing the raw signal information, this always becomes impossible, which is why, as I say, it's really important instead to build in procedures that error check. Take 2 shots always on all your points that you're surveying. Dump your satellites, regain ambiguity so that you can check. Have your check-in point, have your checkout point. That's the most important. Donald's asked to give a quick workflow of doing a 20 by 50 meter cadastral survey. So Donald, I'm assuming like you're just surveying a lot is what you're looking for?
Yes, correct. We normally have to report true north and give ground distances in our cadastral plan. I'm particularly concerned about this aspect.
And what is true north?
Right, that would be not grid north. So true north to I guess the meridian, if that's
astronomical north.
Yeah, that right.
And so do you usually have another surveying plan that shows a bearing of some monuments that you're using?
That's correct. Usually a lot of our cadastral plans are referenced.
Yeah, so you've got an assumed north, right?
Mm-hmm.
So usually the way that we see cadastral surveys being done, like if you're doing a lot survey or a subdivision survey or something like that, what you would end up doing is you set up your base station in one place. As I say, I usually always let it collect data while I'm surveying because I will intend later to put it through PPP for my own sake that I've got an independent coordinate for this whole network, regardless of what I'm actually doing. So in my practice, I gather all the survey data together and I'm trying to build a massive cadastral database so that I don't have to resurvey stuff in the future. But for this particular subdivision, what I would do is I would use base station. I'd find 2 pins or 2 monuments from another survey that have an assumed bearing and distance. I would tie in those two points. What I would end up doing is, depending on my data collector, let's assume that my data collector doesn't have a localization function, but I can get UTM coordinates out of these 2 points. So what I would do is I would take, okay, I have point 1, I have point 2, I have the UTM coordinate of 1, I have the UTM coordinate of 2. I can inverse between those 2 coordinates to come up with the grid bearing. I would compare that grid bearing to the bearing shown on a prior survey. So now I know how much I'm going to have to rotate everything. And you could argue, well, the bearing on the prior survey plan might be incorrect. That's fair. Depending on your jurisdiction, sometimes I have to use an assumed bearing. If I need it, as Kamal says, to be true astronomic, then I can actually do a little bit of a slightly complicated calculation where essentially I can calculate what the convergence is from the map meridian that I'm working with against the astronomic meridian that I want to. So I've got an additional little correction to all my bearings. And then the ground distance, I'll use a scale factor based on essentially the mapping scale factor that I'm at, along with that ellipsoid to ground correction. What I won't do is I won't scale my survey based on the shown distance between the two pins, because I find that historical surveys, bearings tend to be very accurate, but distances tend to be very inaccurate, right? So so usually what I use the prior survey to control the orientation, but I use basically the mathematical grid to ground to actually scale my GPS survey up to ground for the rest of the cadastral work, if that makes some sort of sense. And then Stephen hits Stephen hits the nail on the head. It's all about checking, rechecking, and checking a third time from some other direction. So, all right, folks. Well, as I say, I really appreciate all the questions. If there are more questions, please do feel free to reach out to me. I always do like to talk about this, and I'm really interested in hearing about land surveying and other jurisdictions. And otherwise, everybody, please have a good evening.